Very warm welcome to all of you for this in this entire session around smart grid and power generation. The subject of this technical discussion is more around smart grids and power generation. Uh, Before I ask the experts to discuss their technical subjects and presentations, I'd like to invite my co-chair, Professor Mishra, to give a background and the context of this technical session. Specifically, sir, you have great experience in smart grids. If you can give us an overview of what's happening, what's the problem statement that we are going to solve, and any insights from your work in smart grid space.
When we talk about a grid exists today, was there yesterday, and will be also there tomorrow. In the adjective what we have put to it is the smart, and the smartness varies from country to country, person to person. Like when a human being is there and we see another person, we say he is a smart person. It is a relative one, and hence it is country specific. Whatever smart is for United States or maybe for China or maybe for Germany may not be a smart for us, and vice versa. In the contextual sense. In the context of Indian case, if you see, we have lot of opportunity in the renewable. Specifically, we have opportunity in wind and solar, but we have limitation in the storage category. These two renewables are uncertain and unpredictable in many cases. Because of this reason, we are looking for storage, and in the storage, battery storage is coming up. However, chemical storage is very, very difficult to go into large scale. Therefore, the main focus again in the grid perspective is going into pump hydro. Similarly, the gravity storage is coming up, especially in the context of closure of the mines. We have many underground mines, and all those mines can be used for the purpose of gravity storage. So gravity storage and pump storage in megawatt scale will come. However, hydrogen also will play a big role in the perspective of storage. In the case of hydrogen, when we talk, it has multiple type or nature based, and different countries have different colors given to them. There is no perspective for that. However, the natural hydrogen, which is not yet been evaluated in a big way now, will play a big role in future. So green hydrogen as well as natural hydrogen will come into picture.
So, but from smart grid perspective, you are saying that it's more around investments in storage and how do you absorb and flex the grid. And
So basically, when we talk about smart grid, the generation more focused towards renewable, and maybe the distributed energy resources.
yes,
And
yeah.
in the distributed one, the small breeder reactor may play a big role as well in future. In the perspective of storage, it will be again small scale and large scale, hydrogen, battery, and in big scale, the gravity based storage. In the utilization, again, it will be all power electronic based utilities and power electronic based devices. All these power electronic based devices has characteristics which, if it is not controlled, they will be a demon to the grid. If it is properly regulated, they will be god to the grid.
Okay, so just one last before we move to the panelist, in the interest of time, sir. Uh, how ready we are from our grid perspective, considering 500 gigawatts of RES to be going live by 2030 and another 100 gigawatt of storage. What investments, how ready we are, and what investments we need to do to be able to absorb that kind of storage and renewable?
See, when we talk about large scale power, then power need to be utilized also. So in that case, we need huge transmission network. And transmission network, when we see, it has its own stability problem. It is not simply the production of power, it has a grid stability issue also. And in that context, it is not simply the investment, it is also the technology, policy, demand side management, all things has to come in together. Then only we will be ready to accept this high penetration of renewables.
But you think there are some areas to focus on, or we are on the right track in terms of the existing policy?
So my suggestion is, it has to be a proper policy level decision. It is to be accepted by the community. That means a capacity building as well as a training and the society acceptance need to be there for this large scale penetration for proper utility. Otherwise, like many states now, they have not allowing the solar energy go to the grid.
Yes,
They have
curtailments. Yeah.
zero grid feeding policy.
Yes. Thank you. Very nice to set the context with smart grid. Thank you, sir. I'll just stay with us. I will come back to you if time permits. Let me move to my experts on the left. Maybe if I mean, I'm just trying to understand that, there are a variety of skills that we have on the panel. So maybe it will be a good idea to start with Nilesh. Nilesh is head of operations in India. He represents Nedstack Fuel Cell Technologies. Nilesh, I understand you have a presentation as well. So if you can just take us through some literature that you have brought today and share some knowledge around fuel cells. You can take the podium, please.
Hello everyone. I believe you guys are tired now and I can hear the big sound coming from the diesel generator, right? So it's not irritating, but yeah, this is what we are going to discuss here at this platform. So I represent Nedstack Fuel Cell Technology. It's a Dutch company. It's a Arnhem-based, Netherlands-based company, and we work on the fuel cell technology. So I believe some people know about the fuel cell. So fuel cell converts hydrogen into electricity, and the byproduct is oxygen and water. This is very simple, and if you know about electrolyzer converts water into hydrogen and oxygen. So fuel cell is quite reverse. So we have a manufacturing plant in Arnhem, which a megawatt scale manufacturing plant. We manufacture from powder base to a system base. So our bipolar plates are graphite based, and we are doing this work for more than 25 years now. So here a bit structure of fuel cell. If you see the image here, fuel cell is like a 7-layer assembly. Okay, it comes with a membrane, cathode, anode, and carbon papers and bipolar on the both side. So it's like hydrogen is coming from one side, oxygen mean air is coming from the other side, and it reacts with the membrane and produces electricity and oxygen and water at the other end. It's like a tailpipe emission. If you see why India needs it now, because I'll just move to the next slide. You can just read the text here, because I'm not going to read everything. If you see this graph, this is again this is from the government website. The black portion is covered by the coal electricity. Okay, we are not targeting almost 100% of this electricity to be converted on hydrogen. We are targeting a very small percentage of electricity production through hydrogen, and this is really possible in India, considering our the national hydrogen scheme. Government is pushing for PLIs, subsidies. A lot of hydrogen valley projects are there. So I believe this project, this fuel cell technology will help companies to reduce carbon emission. So I have had, this is again from the government website data. All these blue dots are solar plants. Then some of the yellow dots are hydro plants. This is available on the, I think, Niti Aayog website. What I am proposing here, in hydrogen, everyone is talking about the off-takers of hydrogen, okay? And we have ammonia tenders, methanol tenders, even IOCL, I think L&T got that 100 megawatt electrolyzer tender. To promote hydrogen technology, I think we should start placing small electrolyzers at all these renewable energy parks where we can convert some of the electricity into the hydrogen. And let's say you are having an electrolyzer at a point A in the middle of the city or outside of the city, and you are transporting the hydrogen to all the different locations, and you can use it for multiple applications. So these are the applications what I was talking about. I will start with data centers now, because data centers are promising business and it's upcoming business for India. We are in discussion with a lot of companies for the data center and how we can, stabilize the grid by using any kind of renewable energy source like solar, wind. We can convert some of the portion from RE source to hydrogen, and these data centers needs, now they are using diesel generators for all the spikes going up, during the working hours. So now we can tackle all this problem with fuel cells. If you have fuel cell nearby your data centers, you can produce electricity and the emissions are zero. Even you will not hear this kind of sound. Even I was just going back of this pandal, means the temple, these tents. I see line of diesel generator working, and we are here on the India Energy Week. I believe if management decides, maybe next India Energy Week can be run on the green hydrogen, and every company is supporting green hydrogen. And in every renewable conferences, renewable events, I see this kind of work going on, and then people on this stage complaining about the offtake. This is ridiculous. There are multiple applications. You can see the telecom, medical industry, where the power supply is very important. Then residential colonies. I was talking to some big residential builders, and they are also facing problems for the electricity when there is power cut off. So we have a product for that. Then industrial application, what I can suggest is any industry using diesel generators, or if any industry have power demand, like peak power requirement, and if you found there are hydrogen electrolyzers working around, you can tap to the companies, and maybe they can supply you the hydrogen, and this is how you can solve your energy problems. Then maritime is also big sector. Nedstack is known for the maritime industry. We have supplied our fuel cells, megawatt scale fuel cells, to the maritime industry. Then mobility, India is really focusing on the hydrogen mobility project. I see MNRE, ARI, they recently joined hand and they are releasing the tender. And I think heavy transport industry, they have declared some green highways, hydrogen highways, where we can run this kind of buses. I think NTPC Leh project, I think people are going there to see the feasibility of this transportation. Then we also have hydrogen train. I think the project is commissioned, and we are all waiting for the train on the track. Then the transport of, again, methanol and ammonia, we can use the fuel cell there. The last application I will just focus, I see in Goa, everyone is Goa enjoying, beer and seafood. If you go to south part of Goa, there are some restaurants and homestays, and they don't have a proper power supply, and they are facing a lot of electricity issues. So on the the nearby area, they are using diesel power, the diesel power generators. I will also show you the cost parameters. Before going forward, I was just thinking about how I can just give you an example. I have made the DPR for this concept. India is focusing on, I think, maybe next 2 to 3 years, you will see more than 20 refueling stations around in multiple cities. And this concept talks about hydrogen refueling station as well as EV charging at the same station. So what happened when we at hydrogen refueling station, we fill hydrogen gas at 500 bar pressure, and every station is designed for specific numbers of buses to refuel at the station. Let's say I have designed this for 10 buses or 5 buses refueling station, I have placed 1 megawatt electrolyzer nearby. Then what happened, when my last bus is coming to the refueling, that bus maybe, let's say, start from 10 bar pressure to 350 bar, and hydrogen from the high pressure storage bank goes down from 500 bar to 350 bar or maybe 300 bar. Then what happened, let's say you have a renewable power source. I'm taking an example of NTPC Leh project again, because I also working on the project before. When you start electrolyzer again, next day, you have a buffer because your storage is already around 40-45% filled, because you have a pressure in the gas banks, and that gas is useless because your electrolyzer will start at, let's say, 10 a.m. and will stop at 4 or 5 p.m. And the capacity is down because you don't have a storage anymore to store your hydrogen. So here you need to close the electrolyzer plant, and that is again the cost will go up, LCOH, right? So this is, I am focusing now. If we have a fuel cell at the same plant, we can reduce the pressure from high pressure storage, which is 350 bar, to, let's say, 1 bar, 2 bar, 6 bar, and use it for charging the electric vehicles, let's say buses, trucks, or maybe two-wheelers. And if you have application nearby, you can also take a new connection to refuel your cascades, and you can move the cascades to different location where your diesel generators are replacing, right? So this station is smart station, and you are getting a lot of options for hydrogen vehicles and EV vehicles. So some cost parametrics, you guys can just go through the numbers. Okay, I don't have that much of time to go for the numbers, but 1 megawatt electrolyzer will produce around 18 kg of gas per hour. I'm considering 140-150 kg of gas a day. That can refuel around 5 buses. This is just an example, and I will just talk about the fuel cell case here. Imagine you have a 50 kg of hydrogen gas. That means if you multiply it by 33.33 theoretical energy, theoretical efficiency, and our fuel cell efficiency is 52%, you have 865 kilowatt of energy per day at your hydrogen refueling station. And if I place my Nedstack 200 kilowatt fuel cell, and I'm operating my fuel cell at 150 kilowatt power, running for 6 hours a day, you can refuel 6 passenger vehicles, 100 and maybe more than 100 two-wheeler and three-wheeler and one electric bus. So that's why, when I talk to industries about the refueling station, they are saying, no, it's not a cost-effective solution. And we have, means about the funds, there are issues. Everyone talk about the ROI. If I approach a private entity for a refueling station or a fuel cell, but we have to utilize hydrogen in a smart way, like smart grid. Okay, this is also an example of smart grid. I'm throwing some calculation here. If you
Nilesh, last 2 minutes, so please conclude.
Only few slides. So if you check the last table, you see if I have 400 rupees kg of gas, the electricity cost is 23 rupees. And if I have 150 rupees cash, this is not possible at this moment, but the cost is 8.6 rupees. Okay, this is considering the capex and opex, even maintenance. So everyone is just fighting about the energy sources, BESS, diesel, and fuel cell. So what I think is BESS and fuel cells are running on the same track because both are green. The only problem with BESS is we don't have companies manufacturing lithium cells, but fuel cells are very easy to manufacture in India. Second, fuel cells, if you have hydrogen, you can use fuel cell for 24/7. Battery, it is depending on your grid or the solar or RE part. I will just talk about the emissions. If you use diesel, 1 kg, around 2.5, 2.6 kg of CO2 per liter of diesel. Hydrogen, 0. Battery, it depends on how you're charging it. There are a lot of things we can discuss here, but I have a time limit now.
That's fine. I think this is wonderful. Yeah, please.
Yes, you guys can just take a photo. I'm trying to compare fuel cell vehicle versus fuel cell engines. This is also amazing thing that I'm really looking into. If you guys want to discuss, we can discuss after the session.
Hydrogen ICE engine is 350 bar, the one that you showed on the left?
Yeah, so both are running on the 350 bar.
Okay.
It just requires 6 bar or 12 bar of pressure. About Nedstack, I have 1 second. Just give me one second.
Yeah, please.
So these are our projects.
Last 10 seconds, whatever you want to say.
Yeah, this is my last slide. So,
yeah, sure.
So these are our projects. We have already worked on the shipping industry, dredging, data center. That is really amazing. It's for a North Sea project. Hydrogen bus is still running in the Amsterdam road. The corner one is again stationary power for the residential application. So do contact if you need any information from my side. Thank you so much.
Nilesh, thank you. This was very insightful. Please have your seat. I have a lot of questions, but maybe we will wait for the right time. So I'd like to invite, do we have the next presentation loaded? Maybe Mr. Lalwani from Torrent, if you can just help us understand what are you doing in Torrent on the renewable energy. You've heard about Professor Sukumar talking about the disruption on energy storage and the requirement in grid, and then Nilesh talked about fuel cells. But what are you doing? If you can just come on the podium and share your insights, that will be really helpful. Thank you.
Good afternoon, everyone. In Torrent, actually, let me just give you a little bit about the Torrent. Torrent, we are in the business of power generation. We are in the business of power generation. We have almost like 2.7 gigawatt of thermal generation, and almost 1.6 gigawatt of the thermal projects are under execution. And on the gas-based generation is concerned, we have a 2.7 gigawatt of generation, 3 power plants which are in our operation. So all combined together, we have almost 3.5 gigawatt of generation, both thermal gas as well as the coal. And on the renewable, we have a 2 gigawatt of renewable under operation, 4 gigawatt under execution, and we are executing India's largest pump storage project, 3 gigawatt. So that is one of the largest, I think it is the only largest project of 3 gigawatt at the moment. And we have to be expanded to 1.2 gigawatt. So it will be the overall capacity is close to the Mumbai in Maharashtra, 4.2 gigawatt. So this is about thermal generation and renewable generation, and aiming towards almost like a 10 gigawatt by 2030. So this is aim, but parallelly we have started business or the vertical in the green hydrogen that we have initiated some 3 years back. And initially we started because knowing the unknown area of green hydrogen and de-risking our portfolio. Before that, we started the pilot project, a pilot project of 500 kilowatt of green hydrogen, and it was for the proper use case. It wasn't just a pilot, it was directly blending, because you all know in Torrent we have a city gas distribution vertical also. So we have such geographical area in Gorakhpur. So that we have planned a 500 kilowatt green hydrogen production so that we can directly blend green hydrogen in a gas distribution system itself. So that we have commissioned last year, I think 2025. And initially it was almost 6 months of testing and commissioning. The purpose of this meeting is I want to rather bring here the analysis and our learning on the green hydrogen pilot. It is just a sharing of knowledge and our experience I want to share with all those who are here, present here. So why that pilot project was required? Because Torrent we are going with
Mr. Lalwani, you want to, you have some slides also?
Yeah.
Can you?
But it has not reached, this is introduction.
Yeah, sure. So this is the pilot that you want to talk about. Yeah.
So I want to talk about this 500 kilowatt green hydrogen plant, and I will focus on the analysis part, more on the depth analysis part rather than the, because all of you know, but why we have done in the pilot project. First is that about knowing what are the challenges in the design and engineering of the pilot green hydrogen project. That was first, we can get experience on that. Establishing the operational envelope, because hydrogen, you know, it is explosive gas. We wanted to establish an operational envelope which is safe and which can give the desired quality also, purity. So for that we have, that was the second purpose. The third purpose is to know the performance, obviously, and plus how the process variables are impacting its performance. So that was the third. And before we scale up, obviously we have we are aiming to scale up very high, both in green hydrogen as well as the green ammonia. So this project has given us a lot of learning and insight that I would like to share with you. So that I think it is the components are simple. Everyone knows the components. It is an electrical system. The part A is where the electrical supply is converted, AC is converted into a DC. Then for that rectifier is given. From the rectifier, then it is supplied to the stack, that is a electrolyzer, alkaline electrolyzer. And then we have a hydrogen purification system. And after the hydrogen purification, we have a blending unit to blend the gas, that is purified green hydrogen in the gas distribution network. So that is the last blending. So that this is a general, and other the BOP, you know, that was as a known, all the DM plant, cooling system, chiller system, which are the normal BOP required for the green hydrogen plant. So these are the major component. I think every one of you know it is just to bring. Now, what is the analysis we have done? The analysis, you see, the first analysis is, which is most important analysis, and this is based on the real pilot project. I have not captured, and this is purpose of this. We can benchmark our plant whether our specific energy consumption of our electrolyzer, it is matching with a benchmark plant of this size and the capacity. So that whatever that SEC we got, If you see the SEC is close to the, it's at the 80%, it is going up to the maximum, then it's dropping down. And it is a 4.6, around 4.5 to 4.45 to 4.65. It is going up to the, this is a kilowatt hour per normal meter cube. So this is the SEC we got, which is very close to the normal, I think, world standard level SEC, specific energy consumption we got. And this is measured at the, please note down, this is measured at the stake level. It is doesn't include the auxiliary power or doesn't include the other losses on the BOP side. So, but one thing, please note down that one, the curve after the 80% or 75% of load, the SEC is improving. There is a marginal improvement in the SEC. The specific energy consumption drops. This drop is primarily due to the two factors. The ohmic losses are dropping. Ohmic overpotential, which is happening because of the, when the ions moves from the cathode to the anode, there is a friction loss is there. And at this point, the temperature is quite high. It is almost like a 85 degrees centigrade. 85 degrees, the viscosity of the KOH drops. And that friction is less. And this reduces the ohmic losses. This is the reason why we have this trend is changing from 80% to the 100%. So this is we have established, and it is other whatever in the world, what are the electrolyzers are commissioned, the same trend is observed. Number two, the trend is about the this one about H2 in O2 and O2 in the total O2 in H2 and the H2 in O2. This is a trend. If you can see, the blue trend is the H2 in O2. Now this is this is a nature explosive limit, and this is a very major safety factor in the green hydrogen production plant. The explosive limit, the lower explosive limit of 4% hydrogen in the oxygen. So our limit is, we should see that one, we should not exceed this limit to the explosive limit. Normally, if you see in all those who are there in refineries or the petrochemicals, we try to consider that 50% of LEL is our safe limit. So 4% we should not exceed O2, H2 in O2 any time more than the 2%, because 4% is the limit, 50% is the 2%. So that is a safe margin is kept. And we have established this safe margin that we are not exceeding 2% any time. And as whatever you see that an electrolyzer process, between the two cathode and anode, in between there is a membrane, that whatever the ions moves there from the cathode to anode, this hydrogen movement through the membrane is constant. So whatever the drop in the nature, whatever you see, it is nothing but because whatever the hydrogen is moving from membrane to the anode side is constant. The molecules which are moving from one side to other side, they are constant. Because as you increase the load, the total quantity of hydrogen per total volume of the oxygen is dropping because you are increasing the load. So that whatever you see, it is dropping. So this nature is also the purpose of this pilot, which I told earlier also, is to establish whether before we scale up to higher capacity, whether we are getting the desired safe operational envelope or not. This envelope is the safety envelope as well as the performance envelope. Now you can see that other one is of the gas load at how that one flow, GH2 flow increases, and the temperature. Now all you know, those who are in from this field, this process is totally an endothermic process. It is not an exothermic process. The people will ask why the temperature is increasing in this process. Because it has to absorb the heat to activate, to split the water into the two parts, hydrogen and oxygen. To split that one, it has to absorb the heat. But at the end, we are increasing the temperature. This is because there are two losses which are playing. This is ohmic over potential, and then there is a concentration over potential. Ohmic over potential is because as we increase the load on this one, at that time, what happened that losses, that is electrical losses are increasing, because you can say I square R losses are increasing. These losses are increasing, that increases that one, that the losses are nothing but losses are converted into the heat, and heat is increasing temperature of circulating KOH solution. So temperature is increasing because of this, because of the losses. Because if you know that one, normally the efficiency of electrolyzer is around 70%. Thumb rule is normally people are using. 30%, that is, if say suppose it is a 500 kilowatt, almost like a 30% of energy is lost, and but that energy is converted into heat. That leads to, some are obviously is absorbed by the chiller, but some are absorbed by the KOH solution. But again, it is to be cooled in the cooler and outside that one. That is a different, that is a part of the plant. So this is a rise in the temperature. Second one is the cell voltage. Now this is one of the important parameters, cell voltage. Normally if you see, normally everybody is saying that alkaline electrolyzer, they degrade. But how you measure that degradation? Obviously, you are not getting the desired throughput through the electrolyzer, the green hydrogen, you don't get that one. That is the one thing. But one important thing to measure for engineers, for the same current which is there in 25, in next year 26, for the same current, you will get little bit higher voltage. The higher voltage is that shows now my electrolyzer is degrading by this percentage. So degradation is measured by the electrolyzer cell voltage. So that cell voltage, now you can see that when cell voltage, that it is increasing, you know all this neutral voltage is around 1.43. With the entropy, it can become 1.48. With a 1.48, this is at voltage, theoretical voltage, I would say, when the hydrogen generation or hydrogen production will start. At this production, but at the same time, because if you see, if it is a 1.48, then why you are applying 1.94? This is the loss. But this loss is required. This at theoretical voltage, it is just a theoretical. It cannot give you the desired production, because this, for this one, it is 100 normal meter cube per hour is a production rate. If I apply only 1.48, I will not get the production. If I have to apply more voltage, then only that production will start, or it will be faster. So this is the other reason that one we have to apply. But as for the benchmark plant, cell voltage should be 1.8 to 2.1. That is actually the normal benchmark is there, and we were around that one.
Mr. Lalwani, please conclude now. We are short of time now. Please conclude.
Yeah. Quickly,
Just
actually,
run us through your last few slides.
Yeah, last two slides are there.
Okay,
But
sure.
I want to share this knowledge. So
Yeah, sure. Please conclude.
Now, other thing is at a high pressure, if you see, when pressure is increasing, KOH pressure is increasing, then there is a hydrogen, the crossover through the membrane is also increasing. This is one of the important parameter. You know, the sum of the explosion happened 2 years back or 1 year back in the China, when the blast has happened. This is because of this phenomena, when the hydrogen is crossing the anode side and it mixes with that one and then lead to that one. So it's one of the major safety parameter. And if you see, when at this load, we increase that one, H2 O2, it is dropping down. It is going up to the safe limit. And as I said, that one hydrogen to that first one on the pressure, at the high pressure, hydrogen molecules are compressed, actually volume reduced, because you know it is a simple PV is equal to RT, but when you have a high pressure, the volume reduced. And with that volume, the membrane, that pores, membrane is nothing but a lot of pores are there, very small, minute pores are there. And then little hydrogen crosses diffuse through the other side, that increase the volume. That is gives actually sudden rise in this one. So it gives my pressure limits. I cannot operate beyond that one.
So last 10 seconds, sir, if you can just conclude now. Yeah. Is this the final slide? Yeah.
So I will conclude that one. Actually, that one learning is that the most important learning which I share with you. There are some of the because of to safeguard our hydrogen plant. Important is that one differential pressure across the membrane, electrolyzer membrane, should be minimized as much as possible. That is possible if you have good balanced pressure on both the sides of the of electrolyzer, that is on anode side and cathode side, and there is a very delta P across that is minimum, because each membrane there is a one delta P designed for one delta P, where if you exceed that one, then the hydrogen on the other side would be. So good, very good control is required on the differential level control in the electrolyzer plant. This is very important. Number two is on the bubbling management is important. Heat management is important. Heat management, a lot of heat is produced, but it needs to be, you should design in Indian condition, you should design all the cooling system accordingly, so that at least it should not go up to the unsafe limit. So these three, bubble management, which because when you heat that one, bubbles are formed. You have to remove the bubbles. And second thing, the heat management should be good, and the control management should be good. These are the important and if lesson we have learned, and see that when we scale up, definitely we try to mitigate these risks in the bigger projects.
Thank you. Thank you so much. Really nice and insightful presentation. I can certainly say there are a lot of takeaways from this. Especially you have covered a lot of operational insights from your pilot project. We have some questions, but maybe for now we'll move to Surya Ansari from Serentica. Welcome, Surya. Maybe we can just quickly. I will have to cut short your 2 minutes. If
Sure.
possible, try to be within time. Surya, over to you.
Hi everyone. I'll keep the presentation a bit lively because I think everybody is right now dull. So I'm representing Serentica Renewables India Private Limited, and we are one of the largest, fastest growing organizations who have been working with CNI customers, and we are presenting decarbonizing India's industrial future. So these are some of the drivers for the use of renewable energy, because there is an increased demand. Industrial customers, they want to grow, and RE power is competitive. Also, we provide like kind of firm RE tariffs, so that's it's not based on fossil fuels volatility prices. Then we have also compliances based on renewable purchase obligation and green targets, and also green premiums, which usually impacts hard to abate sectors on export competitiveness, which comes due to the carbon border adjustment mechanism and CCA risk. So due to all these factors, RE has been kind of why customers are not only looking from the optics of ESG, but also the need of an R, and also it's competitive with respect to the fossil fuels. But there is a caveat to this, that solar and wind power, it's intermittent, and only you can displace about 25 to 30% of the load. So the excess power, what do you do, which is above the load? So that gap we try to address this, because usually the captive powers, the captive generators, they rely on fossil fuels. So this is just the demand graph, of which about 50% of demand comes from the CNI sectors, and about 25%, which is the light blue one, comes from the hard to abate sectors, which are very energy intensive. Uh, this part is more of the renewable capacity additions that we are, forecasting right now, of which 7% of the CNI consumption is still untapped as of now, and about we are predicting about 2030 there'll be a demand of 117 to 147 gigawatt renewable CNI capacity is expected, and investments about 74 to 93 billion of investments. So some of the PPA tariffs or the agreements between the off-takers or our clients and the renewable developers, it usually falls under broad definition of firm dispatchable renewable energy. But what does it actually entail is like couple of different products that we provide. So towards the left, towards my right, if you see the generic vanilla take or pay has like whatever you generate, you sell it to the clients or the off taker in our case, and there's no penalty that is implied. Then there is 55%. Let's suppose say if you have 100 megawatt you need to deliver, of which 50 megawatt you assure them that you're going to provide a flat load or a power to the consumers, and then if you do not meet that, penalties do apply if you don't meet the threshold. So other products can be peak hour, that means during a particular day period for 4 hours, let's suppose it during the day, you provide them power of, let's suppose say about 100 mega or 80 megawatt power. So for that the penalties they vary. And then as you move towards more firmer power, in terms of now we engage with time block towards the, so the time block period is where we Serentica works with clients to provide more firmer power for every time block. So every time block in towards a day is like 15 minutes each. So for every 15 minutes we have to deliver 100 megawatt, and to ensure these there are penalties that we have to bear. So how do we ensure that that we also meet the client's requirements, is by making sure that we build solar, wind, and energy storage. And how do we do this? This is done by, so this is a typical load profile, I would say, generation profile. So your x-axis is your the entire day in hours, and this is the load on your y-axis. The blue portion which you see is the wind generation, and this yellow portion is your peak hour generation. So this is the client's requirement, which is the threshold that we sign on the PPA. So about 60%, let's suppose say if we have signed, then we have to meet this threshold. And what do? We use batteries, and the excess which has been generated, we use it to offset during our off-peak hours, that is during the day or towards the evening. And the excess part of it is also traded into the market. So there are combination of solutions that we provide. Sorry.
All three, solar plus wind plus storage.
So we use all the three combinations to ensure that firm power is delivered to hard to abate sectors, especially which are very energy intensive in nature. So one of the case studies that we wanted to present was one of the off-takers, Hindustan Zinc Limited. So it's one of the second largest integrated zinc producer, and it has a metal production of annual about 1.1 megatons, and load is currently met by 290 megawatt of captive thermal power plant. So so one of the solutions, our solution, the key principles are based on, first is how do we ensure that the intermittency, let's suppose the local impacts of weather can be mitigated. So we diversify our wind sites to ensure that we maximize the evening and the night peak hours, and also use solar sites during the day. So we can flatten the curve by using battery storage. The second is, of course, our modeling. So we leverage very advanced modeling tools like Python for power analysis and Plexos to simulate a lot of data in real time, which are the weather data, for the to understand the nature of the weather patterns, and then how can we provide solution to customers. Then, of course, I've already covered energy storage, but we also do pump hydro storage as well to understand intermittency and firmness. Then the geographic diversification I'll cover later, how we do that. And market trading, wherever the excess we have to, the client doesn't take, we make sure that we sell it into the market. So this is our portfolio. So our portfolio, we have commissioned till date about 1.65 gigawatts of hybrid profile, of which wind and PV, if you see, it's spread into 6 states. Majorly our solar with BESS combinations are in Rajasthan, and Maharashtra and Karnataka would have like a lot of wind potential, but also like we have built in some parts of solar as well. So yeah, and the ready to build assets as of now is 6.5 gigawatt, and ISTS connectivity, that because we usually work on interstate corridor to push power. So these are high voltage highways, you can say, for electric power. So so we've built about a portfolio of about 9.5 gigawatts in about, I would say, last 4-5 years. So that's like a massive growth. So for HZL network, what we have done is our customer can be in any state, let's suppose say Chhattisgarh, okay? So we have built our projects which are multi-located. Multi-located means they are in different sites so that we can harness the potential of the solar sites or the wind potential area. So we first identify those potential area, and then our technical experts, once we analyze all the weather patterns, we co-locate. Let's suppose in this case the solar and the BESS have been located in Rajasthan, and we have mitigated the wind intermittency between 2 sites in Maharashtra and Karnataka. So this is one particular case in terms of how the power flow for the single day looks like for our client HZL. So for 130 megawatt of around the clock renewable power that we are delivering, for which Serentica is delivering about 2 gigawatt of hybrid RE projects that include solar, wind, and 1 gigawatt hour of energy storage. So for this, the PPA, the agreement that has been signed is a time block of 315 megawatt that I need to assure for every 15-minute time block. And what this does, if you can see the orange, oh god, yeah, the orange part of it, if you can see, this is the 60% commitment or the threshold that we have to meet, right? And this is the peak hours during which the solar we are able to provide. So during off-peak hours around 4:30 to 8 o'clock, we do this by using the excess power into the batteries and making sure that we are able to provide firm power during those off-peak hours, which we call as shoulder hours. And similarly, we might have like some kind of off-peak PPAs built out for them. So this gray portion is their coal power. So a portion of it still, base load still runs on coal, but the majority they have been able to cover from, I would say, from RE supply. So this is the largest benchmarking, I would say, industrial case for firm power, especially for mining and metal sector. So what does this look like for future? For future, I would say for RTC, the model just is not about the conversation does not fall into a trade-off between whether it's reliable or whether it's sustainable. Right now, it's the need of the hour. There is a solution that has already been we've been working on, and we've been making sure that even our investors, they have a lot of trust in us. So hybrid solution delivers firm dispatchable power, and it is competitive to the fossil fuel base loads. Second is also that the nature of this power is also the behavior of it is similarly analogous to data centers that we are working on as another pilot that we are running. And for this, because the nature is they have high load factors and they have critical uptime needs during one particular hour, so it becomes ideal case for 24/7 decarbonization. Third is also that the customers want that, you know, the CUF percentage increase. They want 85% kind of firm power that can be delivered to them, so that they can take on incentives. So data centers in different countries have incentives even for the same for the industrial sectors. And what we've seen is that the product is not a cost burden for them, but it's competitive, and they can also meet their net zero targets, which I think some of our panel members in the initial conversation has already covered about CCTS and how we can make it economically competitive. So that can be inbuilt into their net zero targets.
Surya, please conclude. Please
yeah.
conclude. Yeah.
So yeah, I mean, to build this kind of solution, you need not only expertise from modeling and market trading, but also to build a portfolio across and understanding how that can work. So for any RTC related or solutions, or if you want to have a conversation, I can take it up later. Thank you.
Next in line, Badri from Fichtner. Badri, welcome again.
Good afternoon, everyone. So I'm Badri from Fichtner Consulting Engineers. We are a global consulting firm specializing in engineering and management consulting services across feasibility, detailed engineering, project management services for generation, transmission, distribution, solar power, battery storage, green hydrogen, electric vehicles, and so on. So today I'll be presenting a case study based on a planning study that we executed for an educational institute that is located in a region with unstable electric grid. So we provided a solution to increase the resilience of the campus power network using grid forming inverters and rooftop solar and battery storage. So educational campuses, especially those that are in regions with unstable grid, they face frequent power outages, which will affect learning, security, essential services such as water, and so on. So conventional grid-connected solar inverters, they are mandated to shut down during grid outages for anti-islanding protection. So these institutions would be without power even in daytime when they have both solar as well as battery storage. So this problem needs to be solved, and we have a microgrid solution by integrating grid forming inverters with rooftop solar and battery storage. So these inverters can supply their own voltage and frequency to the solar inverters, and they can enable them to remain in operation, and they can automatically switch from being in outage to normal operation. And we also use smart load management to prioritize critical demand. So there are a certain demand which is very critical, and there are other demands which are subcritical and non-critical. So this will help us to reduce the quantum of battery storage that would be required. Yeah, so this is the case, the details of the case study. So we have a college campus with about 1 megawatt of rooftop solar, and it's experiencing around 65 hours of outages per month during the summer. So we performed walkover surveys, energy audits, to understand and to inform the design. And this, as I explained, the identification of critical, subcritical, and non-critical loads. So subcritical loads would be something like servers, LAN, laboratory. Subcritical would be something like refrigerators, and non-critical would be elevators, air conditioners, which can be disconnected. So non-critical loads would be disconnected first. They can tolerate extended outages. Then we would disconnect the subcritical loads, and then we would try to provide power to the critical loads for as much as possible. So to implement the load segregation, what we have are critical load panels. So we would have separate circuits for the critical loads, and there would be an ATS, an automatic transfer switch, which would switch to the critical loads during outages. So this is pretty extensive work, which requires a lot of underground cabling and rewiring. So another approach that we could undertake would be using smart breakers, fiber optic networks, and control systems. So we would have controllers which would actually control the appliances directly for more flexible load management. So this is again the grid forming inverters that I talked about. They would integrate seamlessly with both the string inverters, the solar inverters, and the battery storage. And they can provide grid forming support, including black start if necessary. And so our priority would be to charge the BESS when there is solar available. And then if the batteries are charged, then we use the solar to supply the loads, and we reduce our intake from the grid power. Thus, we reduce our bills. And when during the night time, when we don't have solar, we would be working on grid power during normal operations, and during outages, we would be dependent on the battery storage. So we looked at several options for the configuration of the BESS network. So this is one option, is to have a centralized BESS where we would have the inverters, the solar panels, the battery storage, all located in one building, which would have the maximum solar potential, and then there wouldn't be any communication requirement for the other inverters. This is low cost, but it is also restricted. The second is the cluster-wise configuration, where we break up the institute into 2 to 3 clusters of 9 to 11 buildings. And here we would have a communication within the cluster, which would be possible to Ethernet cable. If there are greater distances, then we may require a fiber optic cable. And then we have a multi-cluster configuration, which provides the best solution, but it is quite expensive to implement due to the communication requirements which would be required. Optical fiber cables would be extensively required. And the final is the individual building solution, so which would be each building would have its own sized BESS. This would be expensive because you would have a decentralized BESS, which would be multiple units of decentralized BESS. So we chose option 2, which is the cluster-wise configuration, as a balance between both cost considerations as well as the ease of implementation and the degree of control. And this is relating to battery storage. We could have 2 strategies wherein we have an initial overbuild. As the lifetime of the BESS goes on, or we could have a life cycle augmentation where we start with smaller capacity, and then we keep buying new battery sets. So this is about the calculation of the BESS sizing. So we use the depth of discharge. So for lithium ion, it's quite high, 80%. For lead acid, it's only 50%. So some of the salient features. So the battery inverter would be connected to both the BESS as well as to the string inverters, and the EMS would control the output of the solar inverters, the battery inverters, and the BESS. So basically, the priority of energy, which I talked about earlier, is important for us. And some further details about the configuration. The solar inverter, the output of the solar inverter can be controlled by using system frequency. So the battery inverter would simply increase the system frequency, and this would reduce the output of the string inverters in a proportionate manner. So yeah, so just to conclude, so grid forming inverters can help us solve this reliability issue and make our campus microgrids more resilient. And this solution can be extensively implemented in other sectors such as healthcare, defense installations, industrial parks, and other remote off-grid locations. Thank you so much.
All right. Thank you so much, the entire panelists, sir, and really thankful for being here. To all the panelists, we look forward to seeing you on the other side of the session. Thank you.